Hey guys, and welcome back to another video. So today we're going to be making a compound known as dipotassium phthalate and subsequently producing phthalic acid from that. Now we need the orthophthalic acid for a future reaction, so that's what we're going to be separating also in this video. Now the starting materials for this production, we've actually made some of them in a previous video. If you recall, if you've watched the video, we made some potassium permanganate crystals. Now we only got 6 grams, which corresponded to just over 6% yield, which was very, very, very poor. And that was when we oxidized the, we used potassium nitrate as our oxidizer to oxidize some manganese dioxide and potassium hydroxide. And this formed potassium manganate, which we subsequently put into water. And then we lowered the pH of it and disproportionated it into potassium permanganate, which we boiled down, crystallized out, vacuum filtered off, and purified. And 6 grams wasn't really enough to continue forward with this reaction, so I went ahead and made some more. Now, instead of using potassium nitrate as our oxidizer, I used a far stronger oxidizer known as potassium chlorate and scaled up the all of the reactants. So the potassium chlorate was actually originally made from bleach. If you recall, we also made that in a separate video, and it worked far, far better. I also, if you've watched my video on how to make potassium permanganate, we did it in a tall cylindrical soup can type steel container. And that didn't work too well, so what I decided to do was I took an old baking pan and I did it there because it allowed for much greater surface area and much more even heating. Anyhow, with all of that aside, we now have 55 grams of very nice and pure potassium permanganate crystals, all ready for this reaction. So the corresponding amount of xylene which we're going to be oxidizing with this should be about 12 milliliters, which I have weighed out here. Now this xylene can just be purchased at places such as Home Depot or Canadian Tire or most hardware stores, and it's used as a paint thinner. Now xylene can be either found as xylene or xylol, xylol, and it should be able to be found pretty easily, but sadly we're after the ortho isomer. It has 3 isomers, ortho, para, and meta, and we need the ortho isomer so that we can eventually produce phthalic anhydride. And this xylene contains 20% of the ortho isomer, and the others are the para and the meta isomer. So we're going to need to be separating that, so we're also going to be separating that later on in this video. But nonetheless, we have all the reactions right here. But if we were just to add in all of this potassium permanganate at once, what would most likely happen would be that the potassium permanganate would actually oxidize the orthoxylene to dipotassium phthalate, but then it would it's such a powerful oxidizer that it would actually start to oxidize the benzene rings and totally destroy our molecules, which you really don't want to happen. So we're going to instead be slowly adding our potassium permanganate in via this addition funnel. Now, potassium permanganate has a relatively low solubility of 6 grams per 100 milliliters at room temperature, so we're going to need to be heating this up far hotter. So I'm going to boil some water. All of this 55 grams of potassium permanganate should dissolve in 200 milliliters of boiling water. We'll make sure it's all dissolved, add it to this addition funnel here, and then I'm going to turn on this heating tape. Now this high temperature heating tape will just be on low power, but what this is going to do is it's going to heat up our solution so that the potassium permanganate doesn't crystallize out. So we'll just be keeping this around 90 degrees Celsius. Now if you don't have a heating tape, of course you could use a heat gun or something like that, or a hairdryer even, but even if you really don't have that, I suppose you could add everything to the flask at once. You'd have a decrease in yield, but it would probably still work. Nonetheless, I'm going to go ahead and start preparing everything. So we have our cold water condenser running right now. We're going to add all of our xylene into the flask and begin heating as we dissolve all of our potassium permanganate into 200 milliliters of water, add it to the addition funnel, and begin the slow addition. So I'm going to do all that, get all that ready, and then I'll meet you back. Okay, so as we can see, the reaction is now beginning. And I believe we have begun to reflux our mixture. It looks like it's boiling, but that also might be the evolution of carbon dioxide as we're oxidizing our product, our reactants. Anyhow, it's slowly being added in and everything's looking pretty good. We're just going to continue to let this run until I guess we have all the potassium permanganate added in, and hopefully all the orthoxylenes reacted. So that's what we're going to do, and then I'll meet you back. Okay, so some minor bumping was occurring because it got a bit too hot and the solution was bumping, but That's okay. It seems to have calmed down now that I've lowered the heating, and it's still just boiling away. Now you can see down in the flask, it is turned a bit of a brown color, and so have my fingers because I got a bit of potassium permanganate on them, but that's fine. But the flask is turned a brown color, and this is as manganese dioxide is produced by the oxidation reaction. And you can also notice that the addition funnel is now gone. This is because we had added all our potassium permanganate, so I just took off the addition funnel, quickly replaced it with a stopper, and now we're just letting the reaction continue to boil until it's hopefully complete. And as you can see, it seems to be coming along very, very well. Not totally sure when this reaction is going to be done. There's not been a lot of research on this particular reaction, so we're just kind of winging it here and experimenting, but I'm just going to try to keep going until it looks like there's no more potassium permanganate that's in the solution down there. At that point we should be able to filter off all the manganese dioxide, and then actually make our prepare our phthalic acid from that. Nonetheless, I'll let this continue and tell you what else I do. Okay, so now that it looks like it's mostly done reacting, and I could tell because it looked a lot less purple. As you can see when we pour it, it's kind of hard to tell because of all the suspended manganese dioxide, but the solution is very faintly purple indeed. It does actually look really black because of the manganese dioxide. But once we vacuum filter this, hopefully we'll see all that purple color decreased. You can actually see all the dark, thick manganese dioxide that precipitated on the edge of this glassware. Now, a quick tip for actually removing the manganese dioxide is to simply use hydrochloric acid. Sodium metabisulfite, of course, also works, but hydrochloric acid is far more effective, in my opinion. The only downside is that it generates chlorine gas, which is highly toxic, so this must be done outside. Nonetheless, with just a bit of hydrochloric acid, manganese dioxide stains can be removed from glassware just like that. Anyhow, so we're now going to go ahead, vacuum filter all of this solution, and then I'll meet you back. And we're going to, of course, save the solution that comes through, because that's going to be the solution that contains our dipotassium phthalate. Anyhow, I'll do all that, then I'll meet you back. Okay, so we're inside in the fume hood, and the vacuum filtration has been complete. And as you can see, on the left we have a bunch of manganese dioxide, which was vacuum filtered off, and has formed a fairly thick layer in the glass-fritted Buchner funnel over there. And then in the 1 liter beaker we have our solution, which, as I mentioned before, was actually quite transparent and not pink or not purple at all. Not that deep dark purple that we started out with as our potassium permanganate solution. In fact, this probably only contains a couple hundredths of a gram of potassium permanganate, because its concentration, it can be so little and still be detected. Nonetheless, there's still a bit of potassium permanganate, which will hopefully be destroyed when we add hydrochloric acid to precipitate out the phthalic acid from our hopefully solution of dipotassium phthalate. And I'm just hoping that not too much of our dipotassium phthalate was actually further oxidized by excess potassium permanganate, although I didn't have an excess, but potassium permanganate, hopefully it wasn't oxidized into carbon dioxide, as that would be not very good. Nonetheless, our solution here, it looks very nice. However, because it's pretty, diluted, we had to filter it with some water and stuff. So I'm actually going to boil this back down to 200 milliliters before we add the hydrochloric acid. Hopefully this helps. We'll see what all happens, and yeah. So I'll boil it down to 200 milliliters, and I'll meet you back. Okay, so we took the manganese dioxide. It's just on paper because it is quite pure, and we can actually dry it and reuse it in future reactions. And it's actually more pure than the potted grade stuff we started with. It should be very, very pure, as I did rinse it several times, and that's all it should be, pure manganese dioxide. So let that dry, and I'll use it in the future. But anyhow, back to the reaction. So the pink solution, I took and I boiled it down, and as we boiled it down, it actually became clear. So I guess the excess potassium permanganate, that very small amount left over, reacted or something. And it looks like some more manganese dioxide is kind of clumped up. And now I boiled it down to about 50 milliliters, and we can see we're left with a kind of cloudy solution because there's a bit more manganese dioxide. So I'm just going to quickly gravity filter that through this coffee filter here. And then we should be left with about 50 milliliters, maybe 75 milliliters, of this solution, which hopefully contains our dipotassium phthalate. Then we'll take some 10 molar hydrochloric acid, which can simply be bought at places like Home Depot or Canadian Tire as muriatic acid, and we're going to be taking it, and we'll probably add 50 to 100 milliliters or so of it, and it should precipitate out some phthalic acid, which is insoluble in water. So that should hopefully be what happens. We'll see what happens. But yeah, so I'll grab a filter of that, get some hydrochloric acid, and meet you back. Okay, so we're left with a perfectly clear solution, which looks to be about 60 milliliters or so. And I have just about 60 milliliters of hydrochloric acid, 10 molar hydrochloric acid, right there. Now we're just going to slowly add this, and hopefully we should see a white precipitate of phthalic acid. So, oh, perfect. There's some interesting foaming occurring. Not totally sure what that is, but I can definitely see a precipitate forming. Possibly because we concentrated the solution so much. Nonetheless, I'm going to continue to add hydrochloric acid and stir until no more precipitate forms, and then I'll meet you back. Okay, so we added all the hydrochloric acid. We have this beautiful white precipitate of phthalic acid, and because we use xylene, which contains a mixture of all the different isomers of xylene, we have terephthalic acid, isophthalic acid, and orthophthalic acid, which all precipitated out here, hopefully at least. So 20% of this or so should be our orthophthalic acid, which happens to be very soluble in water compared to the other two isomers. Now, close to the boiling point of water, orthophthalic acid actually has a solubility of about 18 grams per 100 milliliters, which is quite high. And around room temperature, it's actually only 0.6, which makes it perfect to be able to separate from these other isomers of xylene. So, nonetheless, we should be able to now vacuum filter this off to obtain our nice phthalic acid, and then we'll go on to the separation process and try to get us some pure orthophthalic acid, which will then subsequently dehydrate in a future video and form some phthalic anhydride, which is very useful for some other reactions. And who knows, perhaps we'll use the other phthalic acids in future videos also. Anyhow, I'll vacuum filter this, and then I'll meet you back. Okay, so we vacuum filtered everything, and you can see we have a nice white filtrate right here, which is wonderful. That's our phthalic acid. Now, because it was warm, quite warm because it just came off my hot plate when we were boiling it down, when we added in the hydrochloric acid, the orthophthalic acid should have stayed dissolved in solution. Now, because this filter was cold and it was cold outside and we were pulling cold air through the filter, it might have crashed out and joined in with the other two isomers of the phthalic acid, but it might also be in this solution here. Not totally sure. The solution is still slightly warm to the touch, so we're going to stick it in the freezer, cool it really cold down, cool it really, really cold, and then we'll see if we can get any orthophthalic acid crystals to come out of that. If not, we needn't worry because we can take this mixture of the three isomers of phthalic acid and simply take it and heat it up really hot to form phthalic anhydride, as only orthophthalic acid sublimates into the acid anhydride. So, I'm going to put this in the freezer, see if we can get any orthophthalic acid to crystallize out of here, and if not, then I think we'll go ahead and produce the phthalic anhydride. I said we'd produce a phthalic anhydride in a previous video, but I think we might just do it today if we can't get any phthalic acid out of there. I'll show you what I mean in a moment. Anyhow, I'll do that, then I'll meet you back. Okay, so our solution that filtered through was taken, transferred to the freezer, and cooled down to -5 degrees Celsius, at which point it hasn't yet frozen. We can see that salt of our orthophthalic acid, which is precipitated out right to the bottom there, which is exactly what we need. So now I'm going to go ahead and vacuum filter that off, and then I'll meet you back. Okay, so after filtering, it's kind of hard to see, but you can see we have a fair amount of orthophthalic acid right here in the center. Probably shouldn't have put it on white paper, but it looks to be about perhaps 1 or 2 grams. Of course, it's still wet, so I can't accurately weigh it. But as soon as it's dry, I'll be able to weigh it, and we can calculate a percent yield. Then, of course, in the back, I have my drying manganese dioxide, and then the what we filtered off originally from the phthalic acid is the terephthalic acid and the isophthalic acid, which will also dry. And we'll be able to calculate percent yields of everything. Now, because xylene bought in stores is 20% of the ortho isomer of xylene, we could expect that we'll have 1/5 the mass of orthophthalic acid as we will the masses of tera and isophthalic acid. And by the looks of things, that looks about accurate, so I'm pretty happy with this result. Anyhow, I'll let everything dry, and then I'll meet you back as soon as we weighed it and calculated a percent yield. Okay, so I finished fully drying that iso and terephthalic acid, which was sitting over here before, and you can see it's now been transferred into this beaker. And I'll transfer it to a separate storage container in the future. We might maybe use it in a future application for something. Who knows, but these two isomers will be a lot more challenging to separate than the orthoisomer was. So we have about 6.8 grams of our iso and terephthalic acid over here, and exactly 1.28 grams of our beautiful orthophthalic acid right here, which is what we were after. So, based on the starting xylene, with our orthophthalic acid, we got a 30% yield, and overall, including the ortho and the tera and isophthalic acid, we got a 38% yield. So, that indicates that there's most likely still a bit of orthophthalic acid left in that solution, which is why we only got a 30% yield of the orthophthalic acid, because in theory, all the yields of all three should be very, very similar, because they're all came from the same xylene product, and yeah, nonetheless, I'm still very happy with what we got. So, we're going to now go ahead and in a future video use this orthophthalic acid to produce some phthalic anhydride, which will be used to produce some phenolphthalein, which is a pH indicator. Anyhow, that's the plan for that, and as for this, we'll just set that aside, and perhaps use it in a future application. Anyhow, I hope you guys enjoyed, and I'll see you in a future video. Wait, bye.